Hello my friends and welcome back to the Today Machine channel. The Sanders Sea Fury test flight on August 15, 2018, marked a significant technical evaluation of one of the most advanced piston engine fighters ever built. Originally designed by Hawker Aircraft, this Sea Fury was extensively modified and maintained by Sanders Aeronautics for precision handling and performance assessment. Powered by the mighty Pratt Whitney R-4360 radial engine, the aircraft delivered immense torque through its 5-blade propeller, demanding fine control from the pilot during acceleration and climb. The test sequence focused on throttle response, engine temperatures, oil pressure stability, and control surface trim adjustments at varying power settings. Data from onboard sensors were recorded to verify cooling efficiency and vibration levels under race conditions. Engineers also monitored aerodynamic performance, ensuring stability across speed transitions and during high-G maneuvers. Every sound from the exhaust stacks and every propeller pulse reflected the mechanical harmony between engine and airframe. This flight not only confirmed system reliability, but also demonstrated how decades of engineering experience and modern maintenance practices keep this iconic aircraft performing at the edge of its capabilities. An engine end. The first engine run of the R-4360 Hawker Sea Fury Racer Furious represents a major technical milestone in Warbird restoration and race aircraft engineering. The original Sea Fury airframe has been extensively modified to accommodate the 28-cylinder, 4-row Pratt Whitney R-4360 radial engine, producing approximately 4,000 horsepower. Extensive work was carried out to reinforce the engine mounts, adjust the cooling system, and integrate the custom propeller reduction gear for efficient power transfer. During the test, all systems were monitored fuel pressure, oil temperature, and exhaust gas readings to verify stability and proper synchronization of all 28 cylinders. Once ignited, the R-4360 delivered a smooth, steady increase in RPM, confirming successful alignment and tuning. This first run validates the engineering precision behind Furious, demonstrating the seamless integration of classic airframe design with one of the most powerful piston engines ever built. After sitting unused for several years, the 6-71 Detroit diesel marine engine was brought back to life under harsh winter conditions. Temperatures had dropped to -10 degrees Celsius overnight, but by noon, conditions improved enough to attempt a restart. Once the fuel system was primed and a squirrel's nest was cleared from the exhaust, the engine responded after several cranking attempts. Known for its distinctive sound and reliability, the Detroit Diesel 6-71 is a 2-stroke, inline 6-cylinder engine displacing 7.0 liters, widely used in marine vessels, buses, and military applications. It employs a roots-type blower for scavenging air, ensuring efficient combustion and consistent performance. Though the hydraulic governor lacks an idle setting, careful throttle adjustment allowed it to sustain operation. Despite years of dormancy, the engine ran smoothly once warmed, showcasing the legendary durability and mechanical endurance of the Detroit diesel 6-71 Marinin. Union Pacific Big Boy 4014's departure from San Antonio showcases one of the most powerful steam locomotives ever built in full operational form. Designed for heavy freight service across the Wasatch Mountains, the 4014 is powered by a 4-8-8-4 articulated wheel arrangement, enabling exceptional traction and smooth handling of massive loads. As the locomotive departs, the synchronized movement of its dual drive sets and 68-inch driving wheels creates a deep mechanical rhythm. The massive boiler generates over 6,000 horsepower, feeding steam through precise valve timing to each of the 16 driving cylinders. Engineers monitor boiler pressure, lubricator flow, and water level to maintain stable performance during acceleration. Each piston stroke and exhaust blast through the twin stacks signals perfect synchronization of mechanical systems under high load. This departure is both a visual and auditory demonstration of early 20th century engineering excellence, an operational tribute to American steam innovation and precision mechanical restoration. Under a bright Illinois sky, Union Pacific's Big Boy 4014 storms through Elmhurst, a thundering echo of America's industrial glory. Built in 1941 by the American Locomotive Company, this 1.2 million pound 4884 steam giant once conquered the steep grades of the Rocky Mountains. Now fully restored, it tours the nation as a living monument to engineering brilliance. Its whistle pierces the air, the ground trembles beneath its steel wheels, and crowds stand in awe as smoke billows skyward. In that moment, Big Boy 4014 is more than a locomotive. It's the living heartbeat of American innovation and pride. NN. The Shockwave jet truck, built on a modified Peterbilt 359 chassis, achieved a remarkable run by outracing an aircraft on the runway. Powered by 3 Pratt Whitney J34-48 jet engines, originally used in U.S. Navy fighter aircraft, the truck generates over 36,000 horsepower and 21,000 pounds of thrust. It can accelerate from 0 to 400 miles per hour in just seconds, using afterburners that produce massive flames and shockwaves. During the high-speed demonstration, the truck maintained stability through reinforced suspension, precision steering, and aerodynamic control surfaces. As the jet-powered truck overtook the aircraft, its exhaust trail and thunderous roar showcased the extreme engineering and control required to operate one. The Shockwave jet truck is a mechanical marvel. An overpowered Peterbilt 359 fitted with 3 Pratt Whitney J34 jet engines, originally from a U.S. Navy fighter. Generating over 36,000 horsepower, this monster can accelerate from 0 to 375 kilometers per hour in just 6 seconds. Its afterburners shoot flames nearly 20 meters long, producing a thunderous roar that shakes the ground. Built primarily for air shows, Shockwave demonstrates extreme propulsion physics, combining jet thrust, aerodynamics, and reinforced chassis engineering to withstand colossal stress forces. With a parachute-assisted braking system and precision control surfaces, it's not just a spectacle of speed, but a technical showcase of raw power and mechanical endurance. The chill morning air hangs still over Loch Fad as the unmistakable silhouette of the Bluebird K7 rests on the water, sleek, blue, and timeless. Once the fastest hydroplane on Earth, this legendary machine carries the spirit of its late pilot, Donald Campbell, whose relentless pursuit of speed defined an era. Built in the 1950s by Samlesbury Engineering, the Bluebird K7 was powered by a Bristol Siddeley Orpheus turbojet, producing over 4,000 pounds of thrust, a technological marvel designed to skim the surface at unimaginable velocity. Today, decades after its tragic crash on Coniston Water in 1967, the roar of the Bluebird returns. Mechanics and engineers gather along the shoreline of Bute, Scotland, as the team prepares for the engine's startup, a moment thick with emotion and anticipation. The crew checks fuel lines, ignition circuits, and control linkages with quiet precision. A signal is given. The jet ignites with a rising whine, the water trembling under its power. Flames flicker from the exhaust as the crowd erupts in applause, some wiping tears from their eyes. It's not just machinery coming to life, it's history reborn. As the Bluebird accelerates across Loch Fad, its hull slices the surface with grace and fury. The iconic blue paint gleams under the Scottish sun, the sound of the Orpheus jet echoing through the hills. For a few breathtaking seconds, time itself seems suspended. The same spirit of speed, courage, and innovation that once drove Campbell now thunders again. The Bluebird floats gently to a stop, steam rising in soft waves. The crew approaches with reverence, knowing they've not just revived a machine but honored a dream. When the run ends, silence settles over the lake, broken only by the hum of cooling metal. On Loch Fad, the Bluebird K7's final run isn't about breaking records. It's about connection between generations, between man and machine, between past and present. It's a tribute to the unyielding human drive to push beyond limits, to chase the impossible, and to let history breathe once more through fire, water, and jet-fueled thunder. On-wing support maintenance involves performing engine inspection, troubleshooting, and repair directly on the aircraft to minimize downtime and avoid unnecessary engine removal. This field-based maintenance approach enables corrective and preventative actions to be executed while the engine remains installed on the wing. Typical tasks include borescope inspection, hot section repair, compressor and turbine blade blending, accessory replacement, fuel and oil system checks, and minor performance restoration. Technicians utilize OEM-approved tools, calibrated instrumentation, and service data to maintain conformity with airworthiness standards. Each operation follows a defined maintenance work scope, incorporating vibration analysis, temperature trend monitoring, and post-repair functional testing. Engineering support teams provide remote technical validation and documentation for traceability and quality assurance. On-wing support maintenance improves operational availability, reduces turnaround time, and optimizes engine lifecycle cost by addressing technical issues efficiently without major disassembly or transport to overhaul facilities. Untitled Chapter. The Pratt Whitney R-4360 represents the peak of piston engine development during the golden age of aviation engineering. This 28-cylinder, air-cooled radial engine was arranged in 4 rows of 7 cylinders, forming a complex yet highly efficient configuration. With a displacement of 71 liters, it produced between 3,000 and 300 horsepower, depending on the version. The engine powered some of the largest post-war aircraft, including the Boeing B-50 Superfortress, the Convair B-36 Peacemaker, and the Douglas C-124 Globemaster II. The R-4360 featured a mechanical supercharger for increased altitude performance and a sophisticated oil circulation system to manage the intense thermal load generated by its 4 radial rows. Each cylinder operated with dual ignition, 56 spark plugs in total, to ensure consistent combustion and reliable operation under high power. Maintenance crews required specialized training due to the engine's intricate accessory drives, intercoolers, and complex fuel system. And when running, the R-4360 produced a deep, rhythmic resonance unique to its multi-bank configuration. Its massive 4-blade propeller converted raw engine torque into thrust with remarkable smoothness. Even today, restored examples of the R-4360 demonstrate the extraordinary precision and craftsmanship that defined late-era reciprocating aircraft propulsion before the transition to turboprop and jet technologies. NN. The GE90 engine by GE Aviation introduced groundbreaking technology with its first-ever composite fan blades featuring a distinctive curved design. These carbon fiber blades significantly reduced overall engine weight and fuel consumption while enhancing aerodynamic efficiency. Celebrated as an engineering and artistic achievement, a GE90 fan blade was even displayed at the Museum of Modern Art in New York. A major milestone for London's Crossrail project saw the 550-ton tunnel boring machines Elizabeth and Victoria lowered into a 40-meter deep shaft in East London. The operation, requiring one of Europe's largest cranes, involved precision lifting equivalent to 280 London taxis. Conducted under ideal weather conditions, both machines were safely positioned underground. Elizabeth will soon begin tunneling beneath the River Lea toward Canary Wharf, where station preparations include concrete breakout at tunnel eyes. After maintenance inside the station box, both TBMs will continue their drives in. At the Silvertown Tunnel project in London, a 450-ton tunnel boring machine recently completed a rare U-turn operation. Using a specialized air cushion system developed by Herrenknecht and its partners, the massive TBM was rotated within the shaft in just 1 day. The system allowed precise, low-friction movement of the machine, ensuring stability and control during the complex maneuver, an impressive engineering feat in confined underground conditions. The steam-powered snowblower at Bernina Pass represents a remarkable feat of early railway engineering, designed to clear deep alpine snow with precision and power. Unlike a conventional plow that merely pushes snow aside, this rotary snowblower uses a front-mounted rotating drum fitted with helical blades. These blades cut, gather, and propel snow outward through a discharge chute in a high arc. The cutting drum operates perpendicular to the train's direction of travel. Its screw-shaped lamellate perform 3 main functions: shaving compacted snow, transporting it laterally toward the discharge chute, and finally ejecting it using centrifugal force. The enclosed housing ensures efficient snow flow while preventing loss of material. Driven by steam, the rotary mechanism receives its power from a locomotive pushing from behind, as the snowblower itself lacks independent traction. Historically, such machines were crucial on lines like the Bernina, Gotthard, and Lochberg railways, ensuring safe winter operation through Switzerland's most severe mountain conditions. Dieselhouse in Copenhagen serves as a technical exhibition center built around the massive Burmeister and Wain 1932 diesel engine, once the world's largest. This 400-ton, 12.5 megawatts two-stroke engine demonstrates the principles of fuel injection, compression ignition, and mechanical power transmission. Visitors can observe its operation and learn about lubrication, cooling, and control systems. The center also features interactive exhibits on marine propulsion, industrial energy systems, and modern diesel efficiency, offering students a hands-on understanding of mechanical and thermodynamic engineering. A freshly rebuilt Detroit diesel 6-71 marine engine roars back to life in the Fire in the Hole test. This unit underwent a complete teardown and conversion from a right-hand configuration to a left-hand to properly match the vessel's propulsion setup. The core engine, with only one 240 original hours, was meticulously reassembled, block cleaned, injectors serviced, blower resealed, and timing reset to factory specs. Once primed and fired, the 6-71's distinctive two-stroke growl fills the air, proving again why this classic power plant remains a trusted marine workhorse for durability, balance, and raw mechanical precision. During the Ninja H2R dyno test, the motorcycle is securely mounted on a high-capacity chassis dynamometer designed for extreme power applications. The rear wheel is clamped against a heavy roller, while the front is stabilized to prevent lift under full acceleration. Cooling fans simulate airflow to manage intake temperature and prevent heat buildup in the supercharger system. The engine is gradually brought up to operating temperature, followed by controlled throttle increases to monitor fuel delivery, boost pressure, and torque response. At full load, the 998cc supercharged inline-4 accelerates rapidly through the gears, with data acquisition systems recording parameters such as air-fuel ratio, exhaust temperature, and wheel speed. After peak RPM is reached, the throttle is released, and the system enters a controlled deceleration phase. All recorded data is reviewed to verify engine calibration, combustion stability, and mechanical integrity under maximum output conditions. On the vast salt flats of Bonneville, Kawasaki Team 38 pushes the Ninja H2 to its mechanical limits in pursuit of a new land speed record. The conditions are extreme deep ruts, uneven salt layers, and shifting traction that feels like riding over soft, wet clay. At full throttle, the 998cc supercharged inline-4 engine endures continuous maximum load, demanding precise cooling, lubrication, and control. Even maintaining stability becomes a battle as the surface changes with every mile. Riders adjust posture and throttle input constantly to maintain traction. The slightest imbalance in grip can cause the rear tire to spin uncontrollably under the immense power output. Engineers monitor data from each run, boost pressure, engine temperature, and wheel speed to fine-tune performance for the next attempt. Each mile is timed precisely, and the official record is based on the average of 2 runs completed under varying surface and wind conditions. Despite the challenges, Team 38 demonstrates the spirit of engineering endurance, proving that determination, data, and teamwork can push both machine and rider to the edge of physics. ChemSolid by ChemRock delivers advanced mechanical systems for soil mixing and stabilization, optimized for demanding geotechnical and foundation applications. The KSI and KRD attachments employ high-torque, hydraulically driven cutting heads with replaceable tungsten carbide picks, enabling precise penetration and homogeneous mixing of in-situ soil with binding agents. Through the triple soil mixing process, the KSI units create stabilized soil columns for retaining walls, cutoff barriers, and dam reinforcement. The KRD mixers, adaptable to standard excavators, apply the mobile soil mixing method for rapid ground improvement and slope stabilization. ChemSolid's product line has expanded from the KSI 5000 to the KSI 16000 Twin Hydra, featuring dual high-power drives and 4 synchronized mixing blades. Engineered for efficiency, uniformity, and low vibration, ChemSolid systems ensure structural integrity and long-term durability in modern foundation engineering. NNN. The Hyundai Sulzer 12 RTA 96C is a 2-stroke, turbocharged, low-speed marine diesel engine designed for large container vessels. Running at 72 revolutions per minute, the 12-cylinder inline configuration delivers exceptional torque for direct drive propulsion. Each cylinder has a bore of 960 mm and a stroke of 500 mm, producing a total power output exceeding 68,000 kilowatts. At operational speed, fuel injection, scavenging, and exhaust systems are precisely timed by the camshaft-driven control units, ensuring efficient combustion and reduced specific fuel consumption. Engine monitoring systems continuously record parameters such as exhaust temperature, cylinder pressure, and lubrication flow to maintain optimal performance and reliability. The Wärtsilä-winged 14 RT Flex 96C stands as the most powerful diesel engine ever built, engineered to propel the world's largest container ships, carrying up to 16,000 TEU. This 14-cylinder, 2-stroke, turbocharged marine engine measures 26.6 meters in length and weighs an immense 300 tons. Each of its cylinders, with a 96 centimeters bore and 250 centimeters stroke, produces 720 kW, delivering a total output of 8008 kW at just 102 revolutions per minute. This immense torque drives propellers efficiently at speeds up to 27 knots. The skid steer reflex stump grinder by Diamond Mowers is engineered for efficient stump removal in demanding conditions. Its reflex coupler automatically adjusts cutting speed to load, reducing stalling and improving control. Equipped with a heavy-duty flywheel, durable carbide teeth, and hydraulic depth control, it delivers smooth, precise grinding for professional land clearing and forestry applications. NNN. The Liebherr LB44 rotary drilling rig represents the pinnacle of modern foundation engineering, designed for maximum performance, stability, and operational efficiency. With a drilling diameter capacity of up to 3 meters and depths reaching 92 meters, it's powered by a robust V8 diesel engine delivering 505 kilowatts, compliant with Stage 3B emission standards. Engineered for versatility, the LB44 supports multiple drilling methods including Kelly drilling, double rotary head operation, continuous flight auger, CFA, and full displacement techniques. Its rope crowd system provides a 56-ton pulling force, ensuring the full use of the leader's length. A standout feature is the hydraulic rotary drive, capable of 510 Nm torque with automated torque adjustment and continuous speed optimization. The rig's direct-mounted winches, long crawlers, and compact swing radius enhance stability and control. And equipped with the intelligent electronic control system, the LB-44 delivers real-time monitoring, performance optimization, and simplified maintenance. With its quick assembly design, transport-ready folding leader, and durable Liebherr manufactured components, the LB-44 offers exceptional reliability, efficiency, and longevity, an advanced solution for the most demanding deep foundation projects worldwide. In the bustling heart of Puerto Angamos, a monumental engineering operation unfolds, the transport of the colossal Komatsu P&H 4800 XPC electric mining shovel to Minera Escondida. This giant of steel, weighing hundreds of tons, represents one of the most advanced loading machines ever built for open-pit mining, designed for unmatched productivity and durability in Chile's demanding desert environment. Ferrovial's logistics and heavy transport teams undertook the massive task with precision and control. Each component of the 4800 XPC, from the superstructure to the crawler assemblies and dipper handle, was carefully lifted, secured, and positioned on specialized multi-axle hydraulic trailers engineered to carry extraordinary loads across uneven terrain. Using synchronized transport modules, operators maintained millimetric accuracy throughout the route, from the port's narrow lanes to the long, rugged climb toward Escondida mine. The convoy moved at a deliberate pace, coordinated through advanced telemetry and communication systems to ensure safety and stability. This operation was more than logistics, it was a display of modern engineering mastery. As the shovel neared its destination, it symbolized the seamless collaboration between mechanical design, human expertise, and industrial ambition, a journey that marked a new milestone in heavy transport and mining innovation in South America.